learning assessment summary data collection that we do every year for the division, or actually district-wide, not even the division. So, please, one of you do so. Okay, so we got some stuff to do today. If you haven't seen it, I've updated a couple of the typos that were in the exam study guide. They're minor typos, but worth updating. Just understand that I didn't have a previous study guide, so I took some old exam problems, just piled them in there, tried to change some numbers a little bit, and put as much I could think of that you might need to be aware of. So if you haven't looked at it, that's okay too. You've got a day and a half, right? So it's all good. Oh, there's some more stuff from Jeff. I did not get these entered. Okay, so we have a new concept which is going to be a lot closer to what our comfort level is in terms of electricity and magnetism. That's the idea of electric potential, and its relationship ultimately will be to voltage. So, sort of laid it out already, but I'm just going to piece a bit of it together and we'll take it from there. So, by the way, any questions on anything before we get started? Yes, chickens can wear diapers. Okay, that wasn't clear. And it's a cute thing. Okay. Okay, so to begin with, the idea is that electric force in general is a, if you will, a conservative force. Now, I ought to have you just take a moment and sketch down what you remember about the idea of a conservative force, just for you to exactly see. Okay, so the idea is basically, well, it's probably twofold, but we can extend the idea maybe to 3 or 4 different things. So to begin with, all conservative forces have a corresponding or assigned potential energy. And so not all forces innately have a corresponding potential energy. So for the electric force, potential energy, just typically call it U sub E, and I'm going to put a point P here to indicate that that's at a particular point in space. So again, the idea behind potential energy is that when you're at a particular point in space, there's a corresponding stored or potential energy associated with physically being in that particular location. And to this end, then, this will have some important consequences. Now, the second idea behind a conservative force in general, now this, other examples, elastic force has a potential energy. Gravitational force has a potential energy. Any of the strong, weak nuclear forces, so any of the fundamental forces have an associated potential energy. And then elastic is one of the ones that isn't necessarily a fundamental force. Okay? Unto itself. The second idea behind this notion of a conservative force is that as work is performed, and I'm going to put it in parentheses, we've talked all the way back in 211 that really there isn't work performed. There's an associated work when you take a force and it's involved in the movement of some physical system somewhere else. So there's an associated calculated work, but it's not really something that's performed, because work is a number. It's not, its physical relevance is much more sketchy. Okay, so when work is performed with, or associated with this electric force, it is path independent. And this doesn't always seem, it seems very esoteric and doesn't always necessarily seem to resonate as an idea. But essentially, if you start out at, say, some point A, and at point A you've got maybe let's put a charge Q not at point A, and there is simultaneously some sort of electric force exerted on it. That electric force is due to whatever charges are around it. As this charge ultimately moves through space while being simultaneously affected by this disturbance, this electric force, however it gets here, will have the same associated work due, if you will, to this electric force. So if this were, purely speaking, a path taken this way, and if we call this path 1, then we could say the work associated with the electric force, well, it has some particular value. We would calculate that value by evaluating all of the force displacement products as we step along to get there. And we would evaluate this from point A to point B. If the charge were to undergo a different path, but ultimately end up in the same place, the fundamental relationship between electric force and incremental displacement at any particular point along this path would change. And so the function itself might, on the surface, seem different. It might not when you actually evaluate it, because of the dot product between these two. So when they're pointing in the same direction, you have a maximum product between the two. When they're pointing in different directions, you've got a lot smaller relationship between, if you will, my pen's dying on me again. If you were to take a path, say this way, you might have a small dr that's like this, but your E, or your FE, is still pointing this way. So there would be no work associated with this force along this component of the path, if you will. So even though the path might be longer, this component of it, or this little product down here, would be negligible potentially. Maximized along here, minimized along any perpendicular orientation between path and field. Consequence of this, and it's even sort of built in some ways to this a little bit, is that it only depends on the endpoints. So regardless of path taken, doesn't matter. Bottom line, you start somewhere and you end up back there, and you end up at some final destination, regardless of how you get there. Same amount of work. That's why it's considered conservative. It doesn't require a bunch of other stuff. There's a set amount of work to go from one point to another. So that's sort of the second idea in DEPN. And now, here's the thing. We've seen this before. And hopefully you remember this. If you take a mass and put it at a certain elevation, h, if you will, above the ground, there's an associated work with that mass dropping that distance. The work to go from the top to the bottom, if there's a force mg exerted on this mass, the work to get from top to bottom mg, in this particular case, h. If instead you slid it down some ramp, the associated amount of work when it gets to the bottom, and I better make sure I'm talking about mg, is still mgh. Doesn't matter what path it takes to go from top to bottom. In this case, A and B are not necessarily fixed points, but at least with respect to the y direction, this is functionally the same B because nothing happens gravitationally when we're going anyway. Or for that matter, we could take it to there and then slide it back across over there. So we're so inclined. And again, there'd be no work along the horizontal path. Okay, so we've seen this before, and it doesn't matter how steep this is. It's always the same amount of work to get from top to bottom. So it's the same idea with an electric force. Now the calculation is more complicated. Actually, it's not. It's just we made some assumptions about mg being constant and didn't look at the inverse r squared relationship from the center of the Earth. But there has always been a form of that equation that looks very similar to the electric force that we've already sort of seen. So that's the second idea. And then the third portion of this because of this, and because of this, we can ultimately say, and that can, somewhere else because it's a lot. The work associated with going from some point A to some point B will in fact correspond to minus the change in this electric potential energy. Again, if you start here and you end up over here, when you're here, there's a corresponding electric potential energy. When you're here, just by virtue of its location in space and the charges around it, there's a certain potential energy. The work associated with getting there, well, we calculate it. This into itself will correspond to minus the change in the electric potential energy. And this is built in fundamentally to the definition of electric potential energy, or potential energy itself, in terms of how it relates to force. fact, if you were ever to take a class, for instance, in modern physics, any next level class, and for those of you new, I want to point some out. If you end up at Portland State going into engineering, you only need like 4 classes or 3 classes to double major in physics. The cool thing about it is you can't go for a physics degree and double up on your physics classes and use them for an engineering degree. The reason being is that there's a certain accreditation checklist for engineering classes that have to be met. So in physics, some goofball like me will just have some specific things that are more important than others necessarily when they're designing a particular physics class like thermodynamics. Whereas in an engineering class, they have to meet specific criteria, and it's very rigid. On the other hand, if you're already taking the engineering requirements, thermodynamics, statics and dynamics, it will correspond to to mechanics, upper division mechanics, and then the other classes that you also take, they basically lump together and meet a lot of the requirements for physics. So it ends up being optics in the lab, and I think modern physics are the only classes that you need to add if you're going for an engineering degree to get a double major in physics. Which may or may not help you, especially if you're going on to graduate school, it might be particularly helpful. And usually what happens, most people don't finish engineering degrees in 4 years, or if you start as a junior, in 2 years. Because a junior year oftentimes takes a year and a half, 2 years. It's typically expected 16 to 18 credit hours of engineering type classes for 4 straight years, with some electives spewed in there somewhere. That's really hard to do unless you've got nothing else going on in there. And all the classes line up together, meaning on any given term, you take the courses that you're expected to take next. Sometimes classes are only offered once a year. You miss it for some reason, you've got to go all the way around and wait the following year. So it makes it actually very, very feasible to get those extra physics classes in there. Okay? And it's not an argument, I'm not trying to convince you to do it, I'm just saying it turns out to be a relatively easy pathway. Now, having said that, there's another interesting thing about this force when you look at it at a deeper level that is providing this potential energy that's worth noting. If you take this and rearrange it and think about it backwards, every corresponding fragment of work, if you will, dW, associated with this electric force, will correspond to a FDR product over the very small displacement over which you're calculating your work. And again, this would correspond to minus the change in potential energy in an electrical context. Now, if you just rearrange this, then we're left with a very interesting relationship, which basically says that the force, another way of describing the force, fundamentally, is to say it's the rate of change of electric potential energy as you move a charge around in some electric field, if you will. dr. So it's a spatial derivative of the potential energy pointing in the direction of r, and it's minus. So this is kind of a cool thing. In other words, another way of describing force, if you didn't want to think about it on a more fundamental level, stop thinking about it as disturbance, then really what you can think of is that you're basically all of space has corresponding potential energy due to whatever electric charges, whatever the environment is, actually gravitational as well, all of these things. And what we describe as fundamentally conservative forces, as things are moving along in that space, really the forces that are manifest due to all the charges around whatever is going on, and we calculate it from Coulomb's law, really just correspond to how the potential energy itself is changing in space. And so at some point we stop, in physics, you sort of stop talking about forces and just start going more fundamentally into energy interpretations, which is why in high energy physics and anything you see that's sort of modern and relevant in physics, they never talk about forces. They talk about energies and high energy physics, and it's always about energy because we just interpret everything this way. So it's just sort of an interesting side note. But nonetheless, this becomes the important thing. Now, what this means for us, though, is that because of the relationship since an electric force is always interpreted in terms of some affected charge, and how that charge is affected by this electric field, if you will, this implies that if we were to divide out the Q, which is the affected charge involved, and now I probably should have indicated you've got some charge here that's moving around. If we just divide out the Q, then what we're left with is, well, if we have this electric field, and this is, which we define, which we sort of relate to force per unit charge, then there will be a corresponding work as any given charge is moved along per unit charge, which should be related to minus the change in electric potential energy per unit charge to move along in space. And sometimes we refer to this quantity as the change in, or sometimes we just sort of lump the idea of potential energy per unit charge and refer to that quantity instead, since it does not, it's independent of the charge being affected. We refer to that quantity as electric potential change. Or minus the change. So no longer potential energy, it's just the potential until you put a charge there, and then it becomes energy. But the potential is always there. So you can sort of see, it's like capacity, right? Mike Tyson had the potential of knocking somebody out, but it does not until it happens. Maybe it happens more regularly than it should, in the ring or outside. Until it happens, it's just potential. Not even potential energy, it's just potential. So, and because of this minus sign, then we might even extend this a little bit further and say that this is another way of saying wherever you start, minus wherever you end up in an electric potential or in a potential sense. So it's not final minus initial as most change quantities, deltas, are represented. It's initial minus final because of the minus sign. Or if you will, positive work on a positive charge would be going from a high voltage to a low voltage, or a high electric potential to a low electric potential. So if you took a charge, Q naught, at point A, and you move it to point B in some sort of an electric field. Then the work from A to B is greater than zero. It's positive work. In other words, the force associated with the electric field and the electric force that's generated is contributing, not impeding the movement. It's always about, does it contribute in some positive way to what's happening? Or is it just resistive or a drag on the system? But when the work is positive, this corresponds or indicates that you're going from a high voltage to a low voltage or a low electric potential. That should hopefully make some sense, right? It's like a battery. You go from a 9-volt battery, you go from 9 volts to 0, if you will. You go from high voltage to low voltage. It's the direction of path the charge takes. So this ends up being the direction where force contributes to movement. High voltage to low voltage. It tends to be the drift in nature. It's like going from high elevation to low elevation for gravity. So, okay, so this is the idea in a nutshell. The question is, A, why do we use it? And B, how do we use it? And how does it relate back to what we've done before? Are there any questions on this? I mean, the conceptual aspect, it's always the hardest to sort of get your finger on what exactly you understand or don't understand when you think about it. But ultimately, everything from an electric circuit to isolated point charges in empty space act this way. And they follow this basic behavior. One other little thing, and this probably worth noting. When a charge moves in a region where the work, I'll say dW, is always 0, this implies that potential at all points doesn't change. All along that path. And we refer to that path, or to that region where it happens, as an equipotential region. And typically we sort of group where these regions happen to be in space, and we refer to the three-dimensional or the two-dimensional surface in space that corresponds to this to all equipotential paths within that space. We call that an equipotential surface. And when you step off that, your voltage is changing in space, implying that the electric field is associated with stepping off that potential surface. Sort of a side note.